orbit, a unique perspective on the planet. The permanently manned International Space Station circles overhead. It too gives us a unique perspective on science, health, and industry. The benefits of manufacturing in zero-G is spurring other countries and private companies to join this elite club of manned space stations. Low-cost, reusable manned spacecraft is the key to industrial expansion into space. SpaceX, with its Dragon spacecraft and Falcon rocket combination, is fulfilling that need. And other companies will follow.
It will become possible for people, I mean, of course, when I see all this, I've just yesterday seen the Dragon capsule right in front of me. We were able to get closer up to the same level. And I have to say, this is so fascinating. I really would like to step in and sit down and take off. It is a dream for many people.
This is what Dragon is.
Currently, the ISS is the only destination.
Space station and the forward.
The station is 23 years old and is reaching the limits of its ability to service other industrial needs. However, it is imperative to keep the research and science going.
Because we do so much work on the space station, research, experiments that really help humanity, but also give us a different view of our planet. And at the end, we want to protect our planet, and our astronauts are really giving us messages back, which is quite unique and quite nice.
When we look at the science that's done on the space station, it's benefited us on Earth in a lot of different ways. And I think one is a very basic way, in that it's given the opportunity to scientists throughout the world to think about science in a different way. When we think about life as we know it, one fundamental property of all life has been gravity. And one of the first things scientists do is they think, what happens if we take gravity away? And on the International Space Station, we're allowed to do experiments that study just that for long periods of time. So we can study the effect of gravity on things, on people, and then sometimes we can combine that with the effects of radiation. We can also look at, when we think about future space missions, we know that it's going to take a while to get to Mars, and it's going to take some time to get farther. So the International Space Station has given us an opportunity to see what happens when humans are in a space environment or in a microgravity environment where they're in free fall for long periods of time. And this is really important, so we understand the effect of the lack of gravity on humans. We also understand what it's like to be confined in a small environment for long periods of time. And we're starting to understand just the kind of technology we need in order to create safe travel for humans, and also to address some of the challenges in robotic missions far from Earth.
The most recent addition to the ISS, a Russian segment with a European robotic arm, will help alleviate the stretched resources and capabilities of the station.
The ERA arm is completely symmetrical. This means it has a hand or an end effector at both sides, and that each side can serve as the tip as well as the shoulder. So it means that if you have multiple base points on the Russian segment, you can go from one base point to the other, then release your tip or your shoulder, which becomes tip, and then manipulate a payload. So in that sense, it has freedom of motion on the space station.
There's a way to make an entrance.
This is my destiny.
It was now a conspiracy of witches.
Download Veely today.
The robotic arm can be used for example, take payloads out of an airlock autonomously without the risk of an extravehicular activity, for example, and put equipment on the outside. It can be used for inspection. It can be used for putting big new modules, for example, and putting it on the space station, move big things around. And also it can be used to help the cosmonauts when they're doing a spacewalk, to move cosmonauts around or big payloads while the astronauts and cosmonauts have their hands free to work on the outside. So it can be used in several ways.
When we operate the ERA on the ISS, we're obviously going to learn a lot about how to use robots in space. How the robots work in space. We'll have feedback to our engineering process if we finally know what is the performance during its use in space. But we'll also learn on what we can best do with robots, what we can best do with people, and learn about the cooperation. And all of that is going to be very, very useful when we would go further into the universe and still have for sure robots initially, but maybe at some point in time also people with robots. So we're really looking forward to all what we can learn from the experience on the ISS with ERA.
Another addition to the station, delivered by a SpaceX cargo module, is a commercially funded Bishop airlock module. Operated by robotic arms, the commercial airlock allows easy transfer of payloads from within the station to outside for external deployment and to launch CubeSats, which is a burgeoning operational requirement. This will allow for more commercial payload throughput for industrial applications.
One issue that some European scientists worked on is that, first of all, we know that astronauts, after they've been in space for a long time, it's like their sense of taste changes a bit. And the longer they're up there, the more they crave spicier foods or saltier foods. So they start adding more salt to their meals. Well, one of the things that happens as they increase their salt ingestion is that it changes the pH of their blood. It makes it a little bit more acid, not a lot, but just a little bit. And so the body adapts to this acidity by trying to raise the pH just a little bit by providing calcium that comes from our bones. So they actually have increased dissolving of the bones to get that calcium to bring that pH up, but at the same time, we're also seeing that because they don't use their bones very much, because in a microgravity environment, you don't have to fight gravity to stand up straight, that they're already experiencing some bone loss. So we're starting to see that because of this, we're starting to see that this change of taste results in an increase in salt consumption that can actually speed the bone loss in space. So here we're seeing two different effects, and we know here on Earth, we now know that perhaps the increased salt consumption isn't just a cardiovascular effect, but it could have perhaps contribute to bone loss and osteoporosis in humans here on Earth. And we didn't really see that effect until we went to space. The International Space Station provides a platform that we have humans that can act as subjects, but also operators of science. And it's also the only platform that we've had where scientists have the opportunity to do an experiment, see the results, and come back and prepare another experiment. And if something doesn't work, or if they have a second opportunity. And unfortunately, we don't see that with other missions.
What is next? We have now just a bit more than 20 years of ISS operation, very successful, and really incredible science and experiments that have been conducted, and we still learn every single day new things there, and this is really good. So what's next? What will happen is, for sure, that by the end of this decade, we will have commercial space stations up there. There are about 4 projects in the planning today in the US. And the question is, does Europe participate there? Does Europe have its own independent solution? And this is a big question that we need to address. But yes, the space station as we know it today, at the end of this decade, will not exist anymore and will be replaced by some commercial stations. And this is a big change. And Europe needs to be active and show leadership in making this change and really be part of it in this next era, which will come at the end of this decade.
2 commercial projects are well underway to develop commercial stations for industry and tourism. Axiom Space are developing their station to be assembled in 4 modules whilst attached to the ISS. The 4th module will allow the station to deploy its own solar panels and become independent from the ISS. Eventually, Axiom Station will detach and orbit independently from the ISS.
Hi, I'm Gerard Valle, and I'm the Structures, Mechanisms, and Soft Good Lead for Sierra Space Life Habitat. We're really just testing the structural restraint layer, which is what carries the load, and it's 1/3 the size of a life habitat.
So the restraint layer is made up of a material called Vectran. Vectran is an extremely high-strength material, performs really well in this application. It gets us the best performance while maximizing the livable volume inside the habitat.
Pretty amazing.
Sierra Space has been successful in developing their inflatable modules and are also developing their own spacecraft, the Dream Chaser, to service the station called Orbital Reef. First developed in test flight as a crewed reusable space plane in 2013, the Dream Chaser was not selected by NASA in their commercial crew program. However, Sierra Space persisted with an unmanned cargo version and have built 3 so far. The design of the lifting body was derived from an earlier cancelled NASA project HL-20 spaceplane, a concept from earlier lifting body designs like the X-24 and HL-10. To be launched conventionally on a Vulcan Centaur or Ariane space rocket, and to fly back to Earth and land on a runway like the Space Shuttle. The craft will be powered with a vortex engine burning propane and nitrous oxide. It will be able to carry 5,000 kilograms of payload to the orbital reef, and eventually a crewed version will be capable of delivering between 3 to 7 crew or paying tourists. One growing problem, yet to be resolved for these new stations and other orbital assets, is space debris.
The moment, the most known encounters are between active satellites and space debris. An example of such an event happened in 2009, where we had a collision between an active telecommunications satellite, Iridium, with an inactive space debris satellite, Cosmos. So this collision actually resulted in thousands of fragments, and many of them are still in orbit.
The danger of space junk destroying operational satellites and even manned spacecraft is a growing concern.
Space debris is the result of our activities in space. So we have no longer functioning satellites, and we have spent upper stages and the fragments. And in total, we know of about 28,000 objects that we can track, that means follow up from ground. We know of 900,000 objects that are larger than a centimeter. And we know of about 128 million of objects larger than a millimeter. And that shows that the largest contribution in numbers are these small fragments. And unfortunately, collisions and explosions are forecast to continue in space, and that means the population will still grow.
We are launching more and more. In the past, it was only the big space nations, let me call it their way, that were launching. By now, space has been opened up to commercial activities, and therefore we see more and more satellites being launched. Is this an issue for space debris? I would like to say no, if people behave properly. So if we really manage in a proper way the end of life of the satellite, it's not going to be an issue. The point is, will we manage those satellites in a proper way, yes or no? And we see that there is a tendency still to disregard what do I do with my satellite once it reaches end of life, and not consider it since the very beginning. Situation has improved a lot in the past 10 years, but we still have to do some teaching on how important it is to be considered since the very beginning of the design of a project.
Several concepts are in play to remove this orbital debris. For the larger objects, capturing them with spacecraft with arms or grapples, then performing a deorbit burn, dragging the debris down to burn up in the atmosphere. There is another resource available in orbit: sunlight. Why not capture it with solar sails and beam the electricity down to Earth? Massive solar farms comprising of many small mass-produced solar satellites launched into orbit on low-cost reusable rockets. Assembled together in orbit using advanced robotic techniques, and once completed, these satellites will collect the full power of the sun's energy 24 hours a day, 7 days a week, and beam it wirelessly down to Earth to receiver stations, which will turn it back into electricity and deliver it to the grid. Space-based solar power, continuously available, inexhaustible, and sustainable. A scalable energy source that could help meet the world's clean energy goals. Asteroids, remnants from the birth of our solar system. From planetoid-sized monsters down to tiny pebbles, they have orbited our sun for billions of years. We have seen some up close, even touched their surface. We count their numbers, chart their courses, and keep a wary eye on these mountains in the dark. Several spacecraft have ventured out towards these rocky worlds. Some have touched down and taken samples with surprising results, then returned them to Earth. Scientists have found these remnants to be complex and full of secrets. There are different types of asteroids, and 2 new robotic probes are ready to study some of these unique targets. One is called Psyche, and it is perhaps one of the most interesting.
Psyche is an asteroid that orbits the sun out between Mars and Jupiter. It's called Psyche because it was the 16th asteroid discovered, and they were all being named after gods and goddesses at that time.
So the Psyche mission is going to visit an asteroid which is called Psyche. And it is a large metal asteroid, a unique body in the solar system, 150 miles in diameter approximately, and made of 40 to 60% iron nickel metal. That makes it a unique body in the solar system. We visited worlds made of ice and worlds made of rock and worlds made of gas before, but we've never visited a metal world. So we'll get to see something unique and different for the first time.
All the rocky planets that we know of, the Earth, Mercury, Venus, Mars, and the Moon, all have got a metal core in their center. And especially for the Earth, it's the source of our magnetic field, which may be tied to holding onto our atmosphere and making our planet habitable. There's a lot of study that's going on to understand that. But we don't know a lot about our core. What we've learned about it, we learn indirectly because we can't go there. And so Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And so we hope to learn something about what's inside the Earth and other rocky planets by visiting Psyche. But it also tells us about the processes in the very beginning of the solar system. It helps us understand how planets form in the first place.
So the Psyche payload consists of 3 science instruments. One of them is what's called a gamma-ray neutron spectrometer. It's actually 2 separate pieces of hardware. One is the gamma-ray spectrometer and the other one is the neutron spectrometer. Both combined study the elemental composition of Psyche.
If you know the surface composition, what it's made of in terms of iron and nickel and silicon and oxygen, you can then start to say something about its history and how it formed and how it evolved.
By using gamma-ray spectroscopy, we can measure those elements remotely. We don't have to touch the surface. We don't have to dig into the surface.
For Psyche, we're building kind of what we call the Cadillac. It's a very high precision, high sensitivity instrument. It's very similar to the Messenger instrument.
That technology that we developed for the Messenger spacecraft gave us a huge head start going to Psyche.
For our types of instruments, we don't get to fly them very often. So when we actually get selected for something, that's a big deal for us, where we can, take what we learned from the prior missions and implement it now and make an even better instrument.
Only one body like this that's this big and made of metal in the solar system. So the big mystery is, where did it come from? How was it created? One of the theories about it is that it was once the inside of a forming planet, because the planets that we know, Earth, Mars, Venus, Jupiter, have metal cores inside of them. So this may have been the metal core that was forming inside of a baby planet, which then collided with other planets that stripped off, forming planets that stripped off that rocky mantle, just leaving a piece of that core in space. And if that's the case, then by studying this body, we'll be able to study the cores of planets like our own, the Earth, in a way that we can never do otherwise.
Psyche is a larger asteroid in the main belt that is in between Mars and Jupiter. Our experience so far in terms of exploring the solar system has been with either rocky or icy bodies. What's particularly interesting about Psyche is we think it's a metallic object. We have a common understanding perhaps of how regular common rocks behave, but metal behave in a very different way. What I contribute to the mission is trying to understand how cratering and the process of collision and interaction work for a metallic object. And we will use this information then to understand what we see at the surface once we get there. What we did is take an iron meteorite, put it in the chamber and use it as a target for our input experiment. And we were shooting a quartz bit at high speed in order to produce a crater. Everything has been filmed with high-speed cameras, so we have a tremendous amount of data that shows in high resolution what happened during the contact, during the explosion, and how the crater forms on the surface. So everything has been documented in great detail. Here we have a piece of the Gibeon meteorite, and what we see here is a crater that was produced as a result of one of our experiments. And traditionally with rocks, the rim would be blasted away and would be a sort of flattish feature. But here we see these flaps that basically are frozen into place, and this is because the metal is much harder than rocks, and so you can then retain this interesting morphology. There's going to be a very exciting phase of the mission when we actually start gathering data, and there's going to be lots of surprises. I just can't wait to be there and see whether or not there is, any resemblance with this model or not.
There is nothing like the experience of sitting on console on launch day and hearing all the people go around and say, we're go for launch, and then finally getting to say yourself, we are go for launch. It's the culmination of all those years of effort and all those hundreds of people working, and so it's super exciting when you actually, finally say, we're go, and we're gonna get that beast into space. We're going to go launch and do a Mars gravity assist, go by the planet Mars, and then continue on to the asteroid using electric propulsion.
I think no matter what we think it is right now and how much we hypothesize what it might look like, I think it's going to really surprise us and change our views about our solar system when we get there. And that's it's an incredible opportunity to be a part of the team making that happen.
The Psyche mission has suffered several launch delays. However, it should be underway in the next year or two.
Three, 2, 1, 0. Liftoff. Atlas V takes flight.
Another ambitious mission that has launched is Lucy, to study several asteroid targets.
Tower clear.
So Lucy is going to survey 8 asteroids over a 12-year mission life. The first asteroid is in the main belt asteroids. It's Donald Johansen. And then the remaining asteroids are the ones that we call the Trojans. And because we believe that they are remnants of our solar system, by studying their geology, as well as their composition and their mass, then that will give us insight into planets, planet formations, and in particular the outer planets.
The Trojan asteroids, which are located in these Goldilocks zones of gravity-stable orbits or in between the Sun and Jupiter, are really leftover fossils from the formation of the solar system. And these fossils are around 4 billion years old, and when the solar system was forming, they were brought into these locations. And the Trojan asteroids, which have been there since the formation of the solar system, are these last unexplored remnants from the cosmic neighborhood creation. And we're extremely excited to go and visit them because of our total lack of understanding of exactly what is out there. And so it's going to be extremely exciting when the Lucy spacecraft explores them.
Some of the most important planetary science questions we're trying to answer are focused on the origin and the evolution of the solar system. Asteroids and other small bodies are really important keys to understanding that history. Amazingly, many of these mysterious worlds have been altered very little in the 4.6 billion years since they first formed. Their relatively pristine state makes comets, asteroids, and some meteorites wonderful storytellers that have preserved clues they can share with us about conditions in the early solar system. In particular, by studying the Trojan asteroids, we can gain more insight into the history of the outer solar system and the giant planets, Jupiter, Saturn, Uranus, and Neptune. We actually find asteroids across the solar system, including near-Earth asteroids that are in orbits that periodically bring them close to Earth, main belt asteroids that orbit the Sun between Mars and Jupiter, the Trojans that Lucy will explore, and the Kuiper Belt just beyond Pluto, which contains some of the most primitive objects in our solar system. Not all of these asteroids are the same, and Lucy is part of a collection of ambitious missions to study the diversity of these asteroid populations that will help us fill in more pieces of that cosmic puzzle.
Lucy will slingshot out from Earth's orbit and pass by the first target, a C-class or carbon-based asteroid named Donald Johanson after the famed archaeologist. Lucy will continue to the orbit of Jupiter and intercept 4 more targets: Eurybates, Orus, Lucas, and Polymele. Some are D&P-class asteroids never seen before and theorized to be rich in volatiles and organics. The probe will then return to Earth for another gravity assist to the trailing Trojans of Jupiter, intercepting the twins Patroclus and Menetius, more P-class objects.
And Lucy spacecraft was named after the Lucy fossil because we will be studying asteroids, which are the fossils of planet formation. But the Lucy spacecraft and the Lucy fossil was named by archaeologist Donald Johanson and his team because apparently when they discovered the hominin, they were listening to the Beatles song Lucy in the Sky with Diamond. Now we do have a diamond. It's our beam splitter, which is on the LTES instrument, which is used to split the beam, is actually made of diamonds.
My job as a mission architect here at Lockheed Martin, it's very interesting, and it sort of encompasses the biggest picture of the mission. What is the trajectory? What sort of propulsion do you need to fly that trajectory? What does the spacecraft look like? So in the case of, for example, Lucy, it's like, okay, it's going out 5 times further from the sun than the Earth is. And so it's going to need big, huge solar arrays just because of that.
Lucy has 3 scientific instruments on board the spacecraft, and we'll also be using 2 of the spacecraft subsystems to contribute to the science investigation. With the LORRI instrument, we'll be able to get panchromatic images, which will tell us about the geology, and the crater history, which gives us the age of the surface. With the TESS instrument, we'll be able to measure the temperature of the surface at different points, and with the RALPH instrument, we'll be able to measure the composition of the surfaces. The Jupiter Trojans, they have a variety of surface characteristics. They have different colors and different surface compositions, and that leads us to believe that maybe they formed somewhere else.
After launch, the Lucy probe failed to lock one of its solar panels in place. Engineers are working on a resolution to this problem.
The Lucy spacecraft will travel 4 billion miles over its mission. And it is a very sophisticated, well-orchestrated trajectory that gets us there.
I cannot wait for those gorgeous images that our instruments are going to take and bring back to Earth. What that's going to tell me and the world is how gorgeous these objects are, what secrets they have to hold, and it's going to start us unlocking these mysteries of the solar system that are out there. I can't wait, and words can't describe just how excited I am to share with everyone these images when they first come back.
This animation is drawn from the recent data release of the ESA Gaia satellite. It reveals the locations of the larger asteroids within our solar system. This tapestry of orbits shows that several near-Earth objects cross our orbital plane. Geological history records that some have hit the Earth with devastating effects.
We've seen asteroids come through the atmosphere and kind of explode and cause some damage. And thankfully, so far, nothing recent enough that it really has a large impact on our civilization, but it could happen.
There are multiple different ways that you might attack the problem of, oh no, doomsday asteroid is inbound. One of those ways is a kinetic interceptor, which is what DART is working on.
As part of planetary defense, DART, which stands for Double Asteroid Redirection Test, its mission is to impact an asteroid in a binary system.
The reason we're doing this test is to try and prove out the technologies that would be needed to, say, save Earth if an asteroid were coming our direction and we needed to adjust its trajectory so that it would miss the planet.
SmartNav is the autonomous algorithm on board, and the purpose of SmartNav is to identify Dimorphos, which is the smaller of the two asteroids in the Didymos system, and we send maneuver commands to the spacecraft for the spacecraft to hit Dimorphos.
And we understand where about 40% of those asteroids are. We know that no known asteroid is a danger to the Earth right now, but the concern is about the asteroids we don't know about yet. And if we should ever discover an asteroid that's on a collision course with Earth, we want to be able to discover this years in advance so we can give the asteroid a push, not to destroy it, we probably wouldn't be able to do that anyway, but just to prevent that collision. And the DART mission, the Double Asteroid Redirection Test, is our first test of one way of doing that.
Launched aboard a SpaceX Falcon rocket, DART is well on its way to its target.
So the way an ion thruster works is that it utilizes electrical energy to ionize propellant and accelerate it using electric and magnetic fields. What NEXT does is that it increases the power level, you get more thrust out of it, it's more fuel efficient, it lasts longer, basically kind of improves things in almost every way and makes it very beneficial for end users to utilize.
When they're rolled out and fully deployed, they're almost 10 meters long. This is the last time that anyone will ever see these arrays fully deployed. Once we stow them here at DSS, they will not be deployed again until we're in space on the DART spacecraft. Part of our detailed inspection entails Andrew looking at the cell by cell on these arrays, again, that are almost 10 meters long. He'll look at them at different wavelengths of light, different angles, just to assure ourselves that we've found every anomaly possible in these cells and they're fully characterized with the entire array, and we know exactly what we have and the condition it's in when we launch.
DART's going to a binary asteroid, a double asteroid, for two really good reasons. The little asteroid, Dimorphos, which is in orbit around the big asteroid Didymos, That asteroid is about the size of object that we would tend to be concerned about. The most abundant asteroids are the small ones, and this one, about 160 meters across, or about the size of a football stadium, is large enough that it really would cause severe damage if it struck the Earth. Now, by doing our experiment, a kinetic impact experiment on the small moonlet asteroid, we're able to measure our effectiveness in deflecting the asteroid by watching the change in the orbit of the little asteroid around the big one. It makes that measurement a lot more precise and a lot easier to do with telescopes on Earth. The other reason we're doing it is that the presence of the large asteroid there keeps the little one in orbit around it as the pair go around the sun. So that means that this asteroid, which is not a danger to Earth now, will never become a danger to the Earth because of anything that we do in the DART mission. DART is carrying a small CubeSat. It's called the Licia Cube. It was contributed by the Italian Space Agency, and its job basically is to watch the impact from a little distance away. It's riding along on the DART spacecraft, and it's going to be deployed a few days before the kinetic impact. It's going to maneuver and offset itself to the side so that it doesn't run into the same asteroid that DART is running into, and it's got 2 cameras on it that are going to try to first catch the actual impact of DART on camera, but then more importantly, see the ejecta, the plume of material that's blown off the surface of the asteroid and how that develops. If we're fortunate, we'll be able to see the impact crater newly formed by the DART impact. And then, of course, Licia Cube is going to do something that DART can't do, that is fly past the asteroid, look back, and get the full 3-dimensional shape of the object that we hit, which we won't know until we actually get there.
One other threat to Earth is the interstellar object passing through our solar system. They arrive without warning, fast-moving and having no known orbit. Another hazardous mountain in the dark.